Hi everyone, welcome to the new session. In today's session, we are going to speak about very interesting topic, algebra functions. Okay, so let's get started. Okay, let's say that, or let's take two functions. Okay, so here I have taken two functions. My first function is fx, my second function is gx. Okay, so this is the definition of the function. This is the mathematical definition of the function. So I have represented both these functions mathematically. Okay, what does it mean? Let's say that if f is a function and it is a function such that it is defined from a to b, so it means that your a is referred as a domain, and B is referred as codomain, right? So I have done the same thing here. In this function, my x represents the domain and R represents the codomain. And here, this function x represents the domain and R represents the codomain, right? Now, I have told you before that codomain is of no significance to us. Why? Because we cannot predict the codomain. Okay, so if someone asks you to find the codomain of any given function, then it is very hard thing. It is impossible to find the codomain. Why? Because the codomain, it has to be defined by the person who will give you the, or who is setting the question, right? But here you can notice one thing, that here we are more interested in domain. If you look at both these functions, you can see that the domains are the same. Okay, the domains are same. Now you can come across the situation where you have two functions and then the domains are not same. Then we are going to discuss that case later. We can do something about it. That's the good thing. Okay, but if your domains are same, then we can perform some algebraic operations on these two functions. Okay, so what algebraic operations can we perform? Operations can be performed on these functions. Okay, so first operation that we can perform on these two functions that have same domain, what we can do is addition. Okay, addition. Okay, so here the first function is fx, here I have gx, so I would say that the addition of both these function, so it is going to be here, this is fx, then can I denote it with small, and here gx small. Okay, so it's going to be, you can write this function as f plus g and here x. Okay, and it is going to be here fx plus gx, or you can also write it as f plus g and x, and it is a function defined from x to r for all x belongs to x, right? So it is simply nothing. I have just added up two functions, and here f plus g, it means f of x plus g of x. Okay, so I hope this thing is clear to you. Okay, because the domain is same, that's why it says that f plus, this is the addition function, addition of two functions, right? And this is a function defined from x to r, and for all x belongs to your domain, right? Then your next algebraic operation that we can define, or that we can perform on these two functions, it is subtraction. And how we can represent it? It can be represented as f minus g x, it's going to be fx minus gx. And the other way to represent it mathematically, it would be f minus gx. It is a function, right, defined from x to r for all x belongs to your capital X. Why? Because the domains of both these functions are same. The domains of both these functions are same, so no matter whatever algebraic operation you are going to perform on both these functions, the domain is still going to be the same. All right? Then the next operation that you can perform here is multiplication. Okay? And how you can represent it? This can be represented as here f multiply g x, and it will be fx multiplied by gx. And the other way to represent it mathematically, this function, it would be f multiply g x. It's a function defined from x to r for all x belongs to x. I hope this is clear to you. Simple. Okay, so I don't find anything complex here. See here, this is just the addition of two functions, and here we have just separated the functions, and in between we just put the plus sign, right? And this is the mathematical representation. So same goes here. Okay, and the last one, what we can do is division, right? So division, you can represent it this way. So here f divided by g x, it's going to be here f of x by g of x. And the mathematical way to represent it as f by g x, it's a function defined from x to r, domain x to codomain r, for all x belongs to x, provided that gx must not be equal to 0 for all x belongs to x. Okay, now this thing is important here. This piece of information is very important. It says that if you have to divide two functions, you have to make sure that this gx, it cannot be 0. It must not be 0, because if this gets 0, then this function is going to be undefined, right? So that's what I have said here, that this is a function. The division of two function is going to be a function defined from x to r for all x belongs to x. Why? Because input will come from the domain, right? Provided that you won't get gx equal to 0 when you give this function any input. Okay, if it comes 0, you have to neglect those inputs. Okay, so that's what it means. Understand? So this is just to show you how to perform algebraic operations on these two functions, right? Now we'll take some questions and then you have more clarity. Okay, and we'll try to take the questions where we have to sort out the domain. Okay. Okay, so the first question, it is I have two functions. Here my first function is f of x equal to f of x is equal to x cube, x less than 1, and here 2x minus 1, 2x minus 1 for x greater than equal to 1. And here I have g of x. Again, it has two definitions. It has two definitions. The first says that it is 3x for all x less than equal to 2. And then the second definition says that this is x squared for all x greater than 2. And we have to find f minus gx and domain. Okay, so that's what this question says. Okay, now see here, this function fx, it has two definitions, right? It has two pieces. Remember, in the previous session, we spoke about piecewise functions, and the reason why we did that thing there is that because our next session was about how to perform the algebraic operations on the functions. So here, it has two pieces, okay? So it is defined, for this function is defined, it has two pieces, so each piece has its own definition. The same goes for this function too. It has two pieces and each piece has its own definition. Okay, so we'll try to observe these two pieces and we'll try to find out how we can develop some kind of correlation among them and how we can sort out the domain. Okay, now if you look at gx, okay, so if you look at this function gx, it is 3x. It has two definitions. The first definition says it is 3x for all x less than equal to 2. Okay, so tell me if I am not wrong. This could be, or I can rewrite this function as what I can do here. So gx, it's going to be 3x. Okay, now x is less than equal to 2. So this is my number line, and here this is 2. Okay, so it says that this function, it's going to be 3x, where in this region means that when x is here less than equal to 2, so here I am putting solid dot. So in this region, in this whole region, the value of this function, it's going to be 3x. Now, if I break this thing into two pieces, what if I say here that this function gx, it's going to be 3x for x less than 1. Why? Because see here, for x less than 2, the value of this function is 3x. That's what the definition says. Okay, so it means 1 is less than 2, so this is also true for x less than 1, right? Because 1 is somewhere here. And I can develop one more piece for this domain 1 and 2. Why? Because see here, what I'm basically doing is that I am breaking x less than equal to 2 into two parts. First part is going to be x less than 1, and the second part, it's going to be x between 1 and 2. Now, see here, I can do that, right? Because these both things means, if I combine these two things, it means x less than equal to 2. So that's what I'm going to do here, is that it's going to be 3x for all x less than 1, and again it's going to be 3x for all x between 1 and 2. Why? Because here 1 was not included, so here I have included 1. Okay, so these both things represent this, which is right. I hope you agree with me. Okay, then I have this thing here. This definition says that your gx is going to be x square for all x greater than 2. Okay, so I have done some modifications here. So let's see what's on the other side. Okay, so now if you look at other side here, I will check what I can do here. Here I have fx, and it's going to be x cubed for all x less than 1. Okay, now see here, why did I do that? Because I want to make things similar. I want to make this function or the definition of this function look similar to this function. Understand? So see here, my domain is x less than 1. Here I got x less than 1. And here the definition says x cubed. That's fine. Okay? But here I have from 1 to 2. But here, again, I will break this thing. So x greater than 1. So what I can do is that x greater than equal to 1. Okay, so again, here, this thing, what I can do here is that I can break it into several chunks, 2 chunks. Okay, one chunk is that I will make things, I will write one definition for this function where x is between 1 and 2, and the other definition which I will write for x greater than 2. See here, it means the same thing, right? Why? Because here x is greater than 1. So basically what he's trying to say is that this is 1. So x goes from 1 to infinity, and here it's solid dot, means 1 is included. So what I have said that between 1 to 2, this is 2, it's going to be x, and when x is greater than 2, the definition is still going to be x. So it means I am just talking the same thing, right? So here, what I will do, here, I will say fx, it's going to be 2x minus 1 when the x belongs anywhere between 1 and 2, right? Both 1 and 2 included. And then the next definition, it is 2x minus 1, where x, it's going to be greater than 2. Okay, so it's just pure modifications. And why did I do these modifications? So that I can correlate the definitions by making the domains of each piece similar to the pieces of other function. Understand? So if you look at domain here for the first piece of both the functions, now what I can do here is that, now see here, if I have to, what I have to find, f minus g, right? So f minus g of x. So what it's going to be? It's going to be, first, let's do it for x less than 1. For x less than 1, okay, for x less than 1, it's going to be x cubed minus 3x. Okay, x cubed minus 3x for all x less than 1. What it's going to be between 1 and 2. So here it's going to be 2x minus 1 minus 3x, which is going to be minus 1 minus x, minus 1 minus x. And the last one for all x greater than 2, it's going to be 2x minus 1 minus x square. Understand? So from here, what I can say that, from here, I can say that your f minus gx, it's going to be this, okay? And you have to find the domain, okay? So this is going to be your domain. Now, if you look at it, x less than 1, between 1 to 2, and x greater than 2 means it is defined for all the real numbers. Understand? So here your domain, it's going to be all the real f minus g x, it's going to be this, and your domain, it's going to be all real numbers. Okay, so that's how you have to do it. Okay, so here the critical thing here is to divide the function piecewise and then work and then figure out how you can correlate the pieces of two functions and how you can correlate those pieces and how you can sort out their domains. Understand? So this is how you have to approach. Okay, we'll take one more question and then we'll wind up this. Our next question is okay, see here, the next question is, this is my fx, this is x square minus 4x plus 3 here for all x less than 3. This is x minus 4 for all x greater than equal to 3, and your gx, it is x minus 3 for all x less than 4, and here x square plus 2x plus 2 for all x greater than equal to 4. Now you have to find f by gx, and you have to also find the domain. Okay, so let's get started. I think if better if we start from here. Okay, now see here, this is your gx. Okay, gx, so gx, I will do some modifications here. Okay, now x less than 4. Okay, see here, the domain, it is represented, the representation, it is done, and it here in its domain I have 3, and here in its domain I have 4. Okay, so I have to sort out these both domains in such a way so that I can get some common ground for both these functions. Okay, so how can I do it? This is 4. Okay, so this function is defined, this is a definition for x less than 4, means that 4 is not included, means here. Okay, so if it is valid for x less than 4, then this definition is also going to be valid for all x less than 3, because 3 is less than 4, right? And this definition is also going to be valid for all x that lies between 3 and 4, right? So basically what I did, I just broke down this interval into two intervals, this interval into two intervals, x less than 3, and one is x between 3 and 4. Okay, and this one, x squared plus 2x plus 2 for all x greater than 4. Now, if you look at this function, now this definition is valid for all the real numbers. You can check it. It includes everything from minus infinity to infinity. I have done modifications. I didn't change the domains. I just rearranged the things. All right, and here my fx, it's going to be, let's see what I can do here. It's going to be x squared minus 4x plus 3 for all x less than 3. That's fine. Here, see, these two pieces, they got the same domain. Okay, and this one I need to work on. So here I can say that this is going to be x minus 4 for all uh, x between 3 and 4, right? 3 included here. For all x for all here 3, right? And also it's going to be x minus 4 for all x greater than equal to 4. Okay, I did nothing. I just broke this chunk of domain into these two parts. Okay, so that, why did I do that? To make it look similar to these two parts. Okay, now what I can do is I can apply the operation f over gx, which is fx over gx, and let's see what it's going to give us. Okay, so see here, when x is less than 3, then it's going to be x squared minus 4x plus 3 by x minus 3 for all x less than 3, right? And then for this interval of domain, it's going to be x minus 4 divided by x minus 3 for all x belongs to this interval. Okay, and the last interval, it's going to be x minus 4 by x squared plus 2x plus 2 for all x greater than equal to 4. Okay, now you can see here it defines all the domain. If you look at the domain of all these three pieces, then it simply tells us that the domain belongs to real number. Less than 3 means minus infinity to 3. This is 3 to 4, and this is 4 to infinity, means all the real numbers. But we have one problem, because when we did this operation, division operation, when we apply this division operation on any two functions, then according to the definition, what it says, fx over gx. Okay, so when we put the division operation on these two functions, then we have to make sure that this gx, it must not be equal to 0 for all x belongs to our domain, right? So if you look at here, because here the domain is the, see here, for this piece number 2, our domain is it is 3 to 4, right? This is close bracket 3 to 4. Why? Because 3 is included. But when we take this value 3, this function is going to be not defined. Why? Because 3 minus 3 is 0. So we cannot afford 0 in the denominator. So that's why we cannot take this 3. So here I have to say that my domain of this function f by g x it's going to be all real number minus 3. Okay, so this is going to be the domain of this function. This is your f over gx or fx over gx, and this is the domain of this function. You cannot take here 3, so I have to remove this 3 from this interval. I have to exclude 3 from this interval. Why? Because taking 3 makes this function not defined. Okay, so this is how we apply algebraic operations on two functions, and this is how we approach the things when we have to add, subtract, multiply, or divide two functions. Okay, so I hope things are the things make much more sense to you, and I'm sure you are able to get what I've said. Okay, so I will see you next time. Till then, take care and enjoy. Bye-bye.